Hello, I'm Mohammad Rabbani, and in this presentation, I want to introduce a new algorithm to find popular locations based on collected trajectories. In this presentation, we will talk about popular locations and analyze algorithms which can help us to find these kind of locations, and then introduce our algorithm to find popular location and compare it with a simple algorithm, and at the end we evaluate our new algorithm and see the results of running this algorithm. Nowadays, with help of tracking devices, we can find moving objects' location and track them. And by tracking their locations, we can reach to some valuable data and study on them. And some field of study that I can mention here are measure similarity of trajectories, clustering trajectories, simplifying them, and finding popular locations. And this is our main subject, and we want to introduce an algorithm to find these locations faster. So now let's see what popular locations are. They are places which are visited by a lot of humans and objects. Places like museums and restaurants and some other places like this. And some applications and systems like recommender systems can suggest these locations to their users. And many algorithms have been introduced to find these locations. And now let's look at some of these. We divided these algorithms into two categories. In the first one, moving objects must stay in a location for a specific duration. And in the second one, staying time of an object is not important. If an object passes a place, that pass will be a visit. And in the first work that we studied, a minimum threshold has been considered for a location that an object should be in there. And after finding number of visit of locations, they will be clustered by SNOT CB algorithm to find these locations, I mean popular locations. And in the next work, Murna Blood and his colleague worked on detecting non-continuous stop for finding popular places. For example, in this picture, our location is this square, and this line is trajectory of an object. And as you can see here, in 4 points intersected the location, and each point shows the entrance and exit. And we have 2.4 entrance, 2.4 exit. In many works, each entrance will be considered as a visit, but in this work, a staying time of an object is important, and it will be considered as a visit. And they considered a place as a polygon, and they considered a minimum time that an object should stay in there, and also the threshold that the object is permitted to leave. And in the last work, very similar to Godmanson's work, but they have used second algorithm to clustering the locations. About the algorithm which didn't consider visiting time, Mr. Bankert and his colleagues considered the popular location as a square shaped, and length of each edge was r, which are visited by k inputs, and they used zipline method to find popular locations. In the second work, a new method has been introduced by Shank and his colleagues, which receives a set of trajectories and a set of popular places, then return the trajectory with a more spatial density correlation to the query places. And now it's time to introduce our algorithm, but before explaining it, we should explain our problem modeling and some concepts which are related to our problem and solution. The first concept is trajectory. A trajectory is made of some nodes and edges, and nodes are connected to each other sequentially, as you can see in this picture. And each node has three attributes: one position number in x-axis, position in y-axis, and stoppage time of the object. And the next one is location modeling. So we model locations like a square or a rectangle. For each location, we have only position of two nodes: bottom left side and top right side. And also we have a minimum and maximum threshold that an object can stay in a location to consider that stop as a visit. And if the difference between entrance and exit time was between these two thresholds, we can increase visit time. The next two concepts are pass and visit. If an object intersects a location from 2 points, we consider it as a pass. But if the difference between the first and the last intersection is between the specified threshold, we consider that pass as a visit. Otherwise, it is not a visit. And last concept here is a segment tree. Segment tree is a digital structure used for storing information about intervals and is a binary tree, and is suitable to solve questions about range queries in logarithmic time. Has three operations: build, update, and query. And to find index of a child of a parent, we can use this relation where n is index of the parent. We solved the problem, popular location problem, with two methods. The first method is a simple method, and in this, each edge of a trajectory will be checked to find an intersection with a location. After finding the first intersection, the time of intersection will be stored and continue to check remaining edges of the trajectory to find the next intersection, and then calculate the difference between these two intersection time, and if it was between minimum and maximum threshold, the number of visits of that location will be increased. So time complexity of this algorithm is not good enough, and it is O(n), and it will take a lot of time to find intersection for many trajectories locations. So to solve the time complexity problem and find intersections faster, we propose a new algorithm which uses segment tree to find intersections. In this method, first, for each trajectory, a segment tree will be created, and each node of them consists of edges of the trajectory. Therefore, first we create a segment tree for x-axis, sort all nodes and create segment tree based on sorted x coordinates, then insert edges into tree, then for each query, all trees, query I mean edge, location, excuse me, for each locations, all trees will be checked and traversed from the root, and if x coordinates of query was in between the range of that node, then that node would be checked to find intersections. After finding the first intersection and the last intersections, if difference between time of intersection is between thresholds, that pass is a visit. Otherwise, is not. And if we want to solve this problem into dimension, we should do above steps for y-axis. So here we want to see an example. The left side is our trajectory and location, and the right side is a created tree from the trajectory. As you can see, our location is bounded between 2 and 5 in x-axis. So we traverse the tree from the root. We'll start from the left edge of the location. 2 is between minus infinity and plus infinity. And we take these two edges. And as you can see in this picture, the left I'm in, we can't find an intersection here. Therefore, we will check the next node, the left child, and 2 is between minus infinity and 4, and here we have an intersection. So the first intersection will be AB at T1, and it's time to check the next edge at number 5, here the right edge. 5 is between minus infinity and plus infinity, and we check these two edge, and we find an intersection between edge DE and right edge of our location at T2. And after finding these two intersection, we will calculate the difference between T1 and T2, and if it was between the specified thresholds, it will consider it a visit and will increase the visit number of visits by one. And how about time complexity of this algorithm? We should traverse the tree, and it will take O log n. And after finding the proper node, we should select the proper edge to check with its intersection with the location. Proper edge I mean here is a edge that its time is greater than the last intersection, and therefore we should search in a proper node, and it will take O log n, and it will be the time complexity of this algorithm. So to evaluate our method, we select T-Drive dataset, which has been gathered by Microsoft and contains 10,357 trajectories. I've selected 100 trajectories, and we evaluated simple and segment tree algorithm with 10, 50, and 100 trajectories. And to generate queries, or let's say locations, we considered four modes in four states. And in sum, we can say that we analyze this algorithm in 12 states. And also we analyze the results from three aspects. In this table, you can see pre-processing and response time of each algorithm after running. As you can see, proposed algorithm responds faster to query locations than algorithm 1, I mean simple algorithm. So in this chart, we analyze average response time of proposed algorithm, and as you can see in this chart, proposed algorithm responds much more faster than simple one. And this chart shows the effect of increasing visits on response time. About simple algorithm, increasing visits doesn't have important effect, but significant effect, but about proposed one, it has more effect and doesn't have predictable behavior, honestly. For example, in 10 and 15 trajectories, by increasing number of visits, response time has increased too, but in 100 trajectories, we see a reduction in response time. And this happened because proposed algorithm reports a number of line segments as one which have intersection with query size, although they did not have intersection with query size. In fact, they have been intersected with lines which created a line the size of the area. And we also analyze the effect of passes on response time when visits are low. And you can see by increasing passes in proposed algorithm, the response time has been decreased. But about simple algorithm, we see increase in response time by increasing number of passes, but slightly. And so in this presentation, we introduce a new algorithm based on segment tree to find popular locations. This new algorithm can find intersections between a trajectory and location in O log 2. And we compare this algorithm with simple one, which its time complexity was ON. And the results show that proposed algorithm responds to queries and locations much more faster than simple one. And at the end, thanks for watching.